Welcome to the lecture on absolute value inequalities. Today we're going to talk about how you can simplify absolute value inequalities. Your solutions are going to be intervals, and we're going to start by first reviewing the fact that absolute value of x, most of you know that probably just takes a number x and makes it positive. However, what it really is measuring is it's the distance that x is from 0 on a number line. So absolute value of x actually measures a distance. And since we know that distances can only be positive or 0, that's going to help us determine these absolute value inequalities. So let's start with a little review here and solve an absolute value equation. If we have absolute value of x equals to 3, then remember that the solutions to that, and there's actually two of them, is that x could be 3 or minus 3. And you get two values. So x could be plus or minus 3, and that would be your two solutions. So that's when we want the distance to be equal to 3 in either direction, to the right of 0 or to the left of 0. Now when we make this into an inequality and ask the question, when is the absolute value of x less than 3, this is really asking the question, when is the distance less than 3? So we want the distance from 0 to be less than 3. Well, we could go 3 to the right or 3 to the left of 0. And if we want the distance to be smaller than 3, then any x's between 0 and 3 would have a distance less than 3. Or any x's between 0 and negative 3 would also have a distance that's less than 3. At negative 3 and positive 3, we would want open circles because those have distances actually equal to 3, not strictly less than 3. So what we get for a solution, when are the distances going to be less than 3, we actually get this inequality, negative 3 less than x less than 3. So any x's between negative 3 and 3 will give us a distance that's less than 3. If we wanted to write this inequality as an interval, this would be the interval negative 3, comma 3 with parentheses because we have open circles at our endpoints. So what happens if we change the inequality to a greater than symbol? Then we want the question, when is the distance greater than 3? So again, we could go 3 to the right or 3 to the left, and we want this time the distance to be larger than that, greater than that. So we would want to pick x's that are greater than 3 or less than negative 3 in order to make sure that the distance that we're measuring from 0 to our x value is bigger than 3. So any of these x's or these x's would have a distance larger than 3. At the two endpoints, again, we would want open circles because there's no equal bar in our inequality. So when we have a greater than symbol, we actually get two intervals. This interval is going to be all the x's that are less than negative 3. This interval is going to be all the x's greater than positive 3. And we want either this or this to occur. So our solution is a union. X is less than 3 or x is greater than 3. And as an interval, this would be the interval minus infinity to negative 3. That's this half of the graph. Union 3 to infinity. That would be this half of the graph. And the word or, remember, means union. And the union symbol is just a U shape. So here would be our solution to the inequality absolute value of x greater than 3. So that's basically how we're going to solve our two problems. If we see less than symbols, then we're going to want to find all the x's in between our two endpoints, the number itself and its opposite. When we see a greater than symbol, then we're going to set up two separate inequalities. We're going to want our x to be less than the opposite of our number over here, or x greater than that number itself. And so we get a union in the greater than case, and in the less than case, this is an intersection or an and case. Remember, the word and means intersection. So we have intersections for less thans or less than or equal to's, and we have unions for ors and greater than symbols. So let's practice this. If we see the problem absolute value of x minus 2 less than 4, then what I like to do here is kind of visualize what's going on. This is basically asking us, when is the distance going to be less than 4? So on a number line, center your 0, and we want the distance from 0 to be less than 4. So I could go 4 to the right or 4 to the left. I want open circles around those endpoints because there is no equal bar in my inequality. It's a strictly less than symbol. And if I want the distance to be less than 4, then I want all my choices to be within these two endpoints. So what we're going to do is we're going to force x minus 2 to be between negative 4 and positive 4. So this basically creates a triple inequality. We want x minus 2 to be between negative 4 and positive 4. So it has to be greater than negative 4, but at the same time less than 4. So there's our intersection right there. Now all we have to do is solve this triple inequality, and we'll have our values of x. Now to solve a triple inequality, remember you want to get an x in the middle by itself. So all we have to do is add 2 in the middle, add 2 on the left, and add 2 on the right. Negative 4 plus 2 is negative 2. In the middle, we just get x, and 4 plus 2 is 6. So visually on a number line, this would be all the x's between negative 2 and positive 6. And as an interval, this would be minus 2, comma 6 with parentheses. Usually in these kinds of problems, you're going to be asked to write your solution as an interval or set of intervals, not as a graph. So get used to using interval notation. Okay, so when you see a less than symbol, you are going to be setting up a triple inequality where you take this inside expression and you basically squeeze it in between the opposite of this number and that same number. So between negative 4 and positive 4 in this case. Okay, so that's when you see less thans or less than or equal to's. You're going to use a triple inequality. When we see a greater than symbol, now we want to know, when is the distance greater than 4? So if you think about your number line and you center 0, we want our distance to be greater than 4. So if I go 4 to the right or 4 to the left, again I want open circles because there's no equal bar in this inequality. And if I want the distance greater than 4, then I would have to pick something over here or something over here. And what do we want in those two regions? We want this expression x minus 2 to be less than negative 4, or x minus 2 to be greater than 4. So what we end up with in this problem, instead of a triple inequality, we get two separate inequalities, one for the left half and one for the right half. Now on the left half, it's going to be that middle expression that was inside the absolute values, which in this case was x minus 2. And if you look on your graph here, we need that to be less than minus 4, less than the opposite of the number we saw originally. For the right half, we want that same expression, x minus 2, but this time we want it to be greater than 4. And we want the union of these two solutions. So all we have to do is solve each of these individually. I can add 2 to both sides and get x less than negative 2. And over here, if I add 2, I get x greater than 6. And there's still that union in between. So on a number line, this would have negative 2 and positive 6 with open circles. And we'd want all the x's less than negative 2 or all the x's greater than 6. As an interval or interval notation, we actually need two intervals. The interval on the left here for the less than negative 2 inequality would be minus infinity to negative 2 parentheses, union, start at 6 and go to infinity. And that gives us the interval on the right. So here's my solution. Notice that these were the same two problems, but they just had different symbols. The first one had a less than, the second one had a greater than symbol. In our answers, we have the same two important points, negative 2 and 6 showing up, but in the less than case, we were getting the inside interval between negative 2 and 6, and in the greater than case, we were getting kind of the two tail pieces. So minus infinity to negative 2 would be the left tail, and 6 to infinity would be the right tail. So less thans give you triple inequalities, greater thans give you two separate tail inequalities. Okay, let's try a couple more. In the next example, we want the absolute value of 3 minus x greater than or equal to 2. So in this problem, what we're trying to find is when is the distance greater than or equal to 2. So we're centering our 0, and we want to go 2 to the right and 2 to the left. This time we get to have closed circles because there was an equal bar in the original inequality. And if I want the distance to be greater than or equal to 2, then I need to pick things over here or over here. And what we want is that 3 minus x to be within that interval. So we're going to set up our two tail piece inequalities that we need to solve. The one on the left requires that 3 minus x needs to be less than or equal to negative 2. Less than because we want to go to the left. And on the right hand side, we want 3 minus x to be greater than or equal to positive 2, so that we get this right hand tail piece. And we want the union of these two solutions. So if we solve, we're going to subtract 3. We get negative x less than or equal to negative 5. Remember that when you solve inequalities, you want to solve for just x, so we need to get rid of that negative. And the one special rule when you're solving inequalities is if you ever multiply or divide by a negative, you have to flip your inequality around. And so here I need to flip because I'm dividing by a negative 1. So this less than becomes a greater than or equal to 5. On the other inequality, we're going to do the same thing. Subtract 3. So we get negative x greater than or equal to negative 1. Divide through by negative 1. We have to flip. So we get x less than or equal to positive 1. And we want the union of those two intervals. So on a number line, x greater than or equal to 5 would be a closed circle around 5, and greater than would be to the right. X less than or equal to 1 would be a closed circle around 1, and less than would be to the left. So there's my two tail pieces that I was looking for. To write my answer in interval notation, the left-hand tail would be minus infinity to 1 with a bracket. The right-hand tail would be 5 to infinity with a bracket, and then I want the union of those two intervals. So greater than symbols or greater than or equal to's are going to give you the two tail piece intervals for your solution. Next example has a less than. Okay, so less thans are going to give us those triple inequalities. The reason why here is because we want to know when is the distance going to be less than or equal to 1. So if we center our 0 and go 1 to the right and 1 to the left, close circles around those 1's because we have an equal bar, and we want the distance to be less than or equal to 1, then I can only be within these two endpoints. So we want our 7 minus 2x, whatever this expression is inside here, to be squeezed in between negative 1 and 1. So we're going to set up a triple inequality. 7 minus 2x needs to be greater than or equal to negative 1, and at the same time less than or equal to positive 1. Now to solve the triple inequality, we want to get x in the middle by itself. So first I would want to subtract 7 in the middle, on the left, and on the right. So we get negative 8 less than or equal to negative 2x less than or equal to negative 6. And then to finish solving for x, we'd want to divide by that negative 2. Notice that we are dividing by a negative, so we have to flip. So if I flip, this becomes 4 greater than or equal to x greater than or equal to 3. Now this should seem backwards to you because the larger number is on the left, 4, and the smaller number, 3, is on the right. So we want to flip it back around. So to do that, we just put the 3 on the left and the 4 on the right, leave x in the middle, but because we switched the endpoints around, we have to flip the inequalities back around. So these greater thans turn into less thans. On a number line, this basically says we want all the x's between 3 and 4 with closed circles. So my final interval would be 3, 4 with brackets. Okay, so less thans give us the inside triple inequality intersection piece, and greater thans give us the two tail pieces. Okay, these next two examples are along the same lines, but you'll notice that the original problems are a little bit more complicated. And what you want to keep in mind first in both of these examples is you must isolate the absolute value first before you start setting up either your two tail piece inequalities or your triple inequalities. So you have to isolate that absolute value first so that you know what you're dealing with. So in this first example, I've got this plus -3 on the side, so let's move that over to the right side by just adding 3. So we get absolute value of 5x minus 3 greater than or equal to 5. Now as soon as I see that, we see an absolute value and we see a greater than symbol, and we have a positive number over here on the right hand side. So visually we want the distance to be greater than or equal to 5. So we're going to go 5 to the right, 5 to the left, close circles, and if I want the distance greater than or equal to 5, then I need to go to the right or to the left, so I need my 5x minus 3, that expression in the absolute value, to be within these two intervals. So this is going to give us our two tail pieces. We need 5x minus 3 to be less than or equal to -5, or we need 5x minus 3 to be greater than or equal to +5. So if we solve, we're going to add 3, divide by 5. So one tail piece is x less than or equal to -2/5. On the other inequality, we're going to add 3. So we get 5x greater than or equal to 8. So our second tail piece is x greater than or equal to 8/5. So on a number line, we'd have -2/5 with a closed circle, and we want all the x's less than or equal to that. And then we'd have 8/5 with a closed circle, and we want all the x's greater than or equal to that. So my two intervals would be -infinity to -2/5 with a bracket, union, bracket 8/5 up to infinity. And there's my solution. Okay, the next example is going to be done the same way. We have this absolute value over here, but there's a -6 off to the side. So we want to isolate the absolute value first, and I can do that by just adding 6 to both sides. So I get the absolute value of 3/5 plus 4x is less than or equal to 5. So this time we want our distance, which is that absolute value, to be less than or equal to 5. So if I go 5 to the right, close circle, 5 to the left, close circle, and I want the distance to be less than or equal to 5, then I need to be inside this middle interval, so we need that 3/5 plus 4x to be squeezed in between -5 and +5. So we're going to get a triple inequality. 3/5 plus 4x needs to be greater than or equal to -5, and at the same time less than or equal to +5. Now to solve this triple inequality, you could subtract 3/5 from both sides, but that's going to give you some fractions. If you don't want to deal with any fractions, you can clear them out right away. Since the only denominator I have is 5, I can multiply every single term by 5. So here on the left, the fraction, the 4x, and the 5 on the right. So as long as I'm doing it through the entire triple inequality, I'm keeping the equation balanced. So let's see what that gives us. 5 times -5 is -25. 5 times 3/5, the 5's cancel out, and I just have the 3 left over, plus 4x times 5 is 20x, and 5 times 5 is 25. So now I have no more fractions to worry about. So now when I go to solve this, I want to get x in the middle, so we're going to want to subtract 3 in the middle on the left and on the right. So we get -28 less than or equal to 20x less than or equal to 22. And then to finish solving for x, divide everything by 20. Now these are fractions that are not reduced. 28 and 20 are both divisible by 4, so if I divide by 4, I'm going to be left with negative 7 over 5. And 22 and 20 are both divisible by 2, so if I divide by 2, I'm going to have 11 over 10. So on my number line, I'm going to have negative 7/5 with a closed circle, 11/10 with a closed circle, and I want all the x's in between. So this is going to be the interval negative 7/5, comma 11/10 with closed brackets around both. Okay? So to summarize so far, we have now solved absolute value inequalities where we had a positive number on the right-hand side, and we had greater thans, greater than or equal to's, less thans, and less than or equal to's. So we had absolute value inequalities compared to a positive number on the right-hand side. In the next problems that we're going to look at, we're going to be comparing an absolute value inequality to a negative number. So if you look at all of these next examples, what they all have in common is that there's a negative number this time on the right-hand side. Okay? Everything else can vary, but if there's a negative number on the right-hand side, we're not going to need to do any algebra at all to figure out what the answer is, because what you want to remember is that an absolute value measures a distance, and every distance is always 0 or positive. You can't have a negative distance. So if I look at this next example, when is the absolute value of x minus 3 less than negative 4? This is basically saying when is the distance less than negative 4. Well, a distance can't be less than a negative because a distance is either 0 or positive. So this can never happen. So for our answer, we would just write no solution. You don't need to do any work at all. You just need to recognize that it is impossible for an absolute value to be smaller than a negative number, because an absolute value is either 0 or positive. So in the next example, this is asking when is the distance 2x minus 5, an absolute value, less than or equal to negative 5? Well, a distance is never less than or equal to a negative because a distance is positive or 0. So this can never happen, so we just write no solution. In the next example, even though this inside expression inside the absolute values has changed from problem to problem, I'm still comparing it to a negative number, and because this is a less than symbol, we're asking when is the distance less than negative 1? Again, a distance can never be less than a negative, so this can never happen, so the answer is no solution. Now if you look at the next examples, how are they different than the last three? The last three we did were either less than symbols or less than or equal to symbols. In the next three examples, we either have greater thans or greater than or equal to's. So that's going to change our solution here slightly. If I have an absolute value greater than negative 1, regardless of what this expression is inside, this is asking us when is the distance, which is this left-hand side, greater than negative 1. So think about that. If a distance is always 0 or something positive, then when is a distance going to be greater than negative 1? Always. Because a distance is always 0 or a positive number, and 0 is bigger than negative 1, and positive numbers are bigger than negative 1. So this is always true. So how do we write that as our solution? How do we write that with intervals? Well, if this is always true for every x, then every x value should work. So all real numbers would be our solution. And how do you write all real numbers as an interval? You say negative minus infinity up to positive infinity with parentheses. So our distance is always going to be bigger than a negative number, so our solution is all real numbers. Okay, let's try another one. Absolute value of x minus 2 greater than or equal to negative 4. So this left-hand side is a distance, always. That's what an absolute value measures. So when is the distance greater than or equal to negative 4? Well, a distance is either 0 or positive. 0 is bigger than negative 4, and a positive number is bigger than negative 4, so this is always true. So our solution is all real numbers, minus infinity to positive infinity. Okay? The last example, again, this inside expression is changing each time, but really we don't even need to look at that because all we're looking at is the fact that this absolute value is getting compared to a negative number. And since the absolute value measures a distance, we want to know when is that distance going to be greater than negative 5, and that's, again, always going to happen since the distance is either positive or 0. So whenever you see an absolute value compared to a negative number, your answer will either be no solution or all real numbers. How do you know which case it is? Well, if you have less thans or less than or equal tos, then your solution is always the empty set. If you have greater thans or greater than or equal tos, then your answer is always all real numbers. And this is whenever you are comparing an absolute value to a negative number. Just look at the sign. Is it less than or is it greater than? And that will tell you whether you should write no solution or all real numbers. Okay, so now we've talked about how you solve an absolute value inequality when the number on the right-hand side is a negative, and in the problems we did up above here, we were solving absolute values compared to positive numbers. So we've done absolute values compared to positives and negatives. The only thing left to consider are absolute value inequalities compared to 0. And these can sometimes be a little bit tricky. Again, we're not going to be doing really much algebra at all for these. We're basically going to be thinking them through. And what you want to remember is that an absolute value measures a distance. So absolute value is always greater than or equal to 0, always. Okay, so that's what we want to kind of keep in mind when we're trying to figure out what our solutions are. So for example, in this first one, we have an absolute value, and we want to know when is it less than 0. So since this absolute value is measuring a distance, we're basically trying to find out when is this distance going to be less than 0. Well, absolute values are distances. So a distance is always going to be greater than or equal to 0 because a distance is always positive or possibly equal to 0. So when is a distance ever going to be less than 0? Never. So this one is going to have a no solution. Okay? So when you're comparing an inequality and you want to know when is it less than 0, that's impossible. So you get no solution. How about if we compare that same inequality and we want to know when is it greater than 0? So this is asking for when is the distance greater than 0? And this one's a little bit tricky because distance we have said already is greater than 0 because it's positive numbers, but there is a possibility that a distance could also equal to 0. So when is a distance greater than 0? Always, except when the distance equals to 0. So when is a distance greater than 0? Every place except when the distance equals to 0. So we need to find out when the distance might equal to 0. So the way that you find out when your distance is going to equal to 0 is you take your absolute value and you set it equal to 0. And when is 3 plus 2x in absolute value going to equal 0? That's going to equal 0 when the inside stuff is 0. So when 3 plus 2x equals 0. If we solve this, this is the only algebra that we have to do, is solving here for x, we get x equals negative 3/2. Now remember, our solution here, when is the distance greater than 0? It's always greater than 0 except when the distance equals 0. So we want to have as our solution the fact that this is going to be all real numbers except this one point we just found, except x equals to negative 3/2, because that's when the distance equals to 0 and there was no equal bar in my original inequality. So our solution is going to be all reals except negative 3/2. Now how do you write that as an interval? Well, you actually need two. If you think about this on a number line, all real numbers would be the whole number line shaded in, except we want to leave out negative 3/2. So we want to put a little tiny hole right at negative 3/2. So to describe this, we can describe the left-hand inequality as minus infinity to negative 3/2 with the parentheses because of the open circle, and the interval on the right is negative 3/2 again with an open parentheses up to infinity. So our answer is going to be those two unioned together. So this is the way we write all reals except negative 3/2 using interval notation. So you can see the difference here. When we had less than 0, we had no solution. When we had greater than 0, then we had all real numbers except when this inside expression equals to 0. So we excluded just that one point. Everything else was going to work. So two very different answers. Okay? So these are kind of confusing because when you have your absolute values compared to 0, there's actually going to be 4 separate cases. When you have less than 0, you get no solution. When you have greater than 0, you get all reals except where that inside expression is 0. And now we're going to look at when you have less than or equal to 0 or greater than or equal to 0. And we're going to get two different answers for these as well. So let's take a look at this next one. We want the absolute value to be less than or equal to 0. So the absolute value is measuring a distance, and we want to know when is that distance less than or equal to 0. Well, is a distance ever less than 0? No. So that can never happen. But a distance can equal to 0. So this never happens except when the distance equals to 0. So it's never less than, but it could be equal to 0. So we have to find out when that happens. So how do you find when a distance is 0 again? You take this inside expression, 3 plus 2x, and you just set it to 0. And if we solve using our algebra again, we're just going to get that same negative 3/2 number that we got before. So what do we write for our final answer? Remember that we said this was never going to happen except at this one place. So this inequality is never true except at negative 3/2. That was the only place when this inequality would equal to 0. It was never going to be less than, but it could be equal. So in this answer, we actually only have one number that works, just this one place where the distance equals 0. So you can either just write x equals negative 3/2, and that's fine, or sometimes we use sets, and we would just say the set negative 3/2 as our final solution. So this just has one number as its final answer. If you compare that to our last example, it's just the opposite. So when was the distance greater than 0? Everything but negative 3/2. And when is the distance less than or equal to 0? Just negative 3/2. So these two solutions are opposites. Okay? Alright, the very last case that we have to consider is going to be when is your absolute value greater than or equal to 0. So this is asking for when is this distance going to be greater than or equal to 0. So think about that. When is a distance greater than 0 or equal to 0? always, because distances are always positive or 0. So this is always the case, this is always true, so we don't have to do any work at all, and we can just immediately say that all x's are going to work. So our solution would be all real numbers. Okay, so the 0 cases here are probably the trickiest because each type of inequality gives you a different type of answer. Sometimes you get no solution, sometimes you get all solutions, sometimes you just get one number, sometimes you get everything but one number. So you kind of have to memorize these 4 cases or else think it through using words like I did here and sort of derive the solution each time. So let's try 4 more examples where we kind of mix these all up so we can review what we just talked about. So in all 4 of these examples, what you're noticing right off the bat is they are all being compared to 0. So these are those 4 cases that we just did up above. So the first one is asking, when is this absolute value less than 0? So when is this distance less than 0? So think about that. When is a distance less than 0? When is a distance negative? Never. So this solution is no solution. Okay, you don't have to do any work. You just have to realize that we're trying to find when is a distance negative, which can never happen. Okay, if we look at the next example, we're comparing it to 0 again. So this is asking, when is the distance greater than or equal to 0? So when is a distance positive or 0? That's always. Your distance is always a positive number or possibly 0. So if it always works, then x can be any real number. Okay? For the next 2, when is your distance less than or equal to 0? So we are comparing this to 0 again. So we want to know, when is the distance less than or equal to 0? Well, start with the less than. When is a distance less than 0? Never. You can never be less than 0 because a distance is positive and less than 0 would be negatives. When is a distance equal to 0? That can happen, and that's going to happen when this inside expression equals to 0. So the solution here is that you're never going to be less than 0, except you could be equal to 0. So we're going to have no solutions except when the distance equals to 0, and that's going to happen when 3x minus 4 equals 0. So if we solve for x by adding 4, dividing by 3, we get x equals 4/3. So we want no solutions except this one point. This is the only place where I'm going to either be less than or equal to 0. And in this case, it's the equal. So our solution is just x has to be 4/3. Okay? In our last example, when is the absolute value of x minus 5 greater than 0? So this is asking, when is the distance greater than 0? So think about that. When is a distance greater than 0? Always, except when the distance might equal to 0. So we have to find out when that happens. When is the distance going to equal 0? Whenever this inside expression equals to 0. So we add 5, and we get x is 5. And now, should our answer be just 5, or should it be something else? Look back at what we wrote up above. We want all x's, because this is always going to work, except when x is 5. So we want all real numbers except x equals 5. So how do you write that? With intervals again, you're going to write all real numbers, but leave a little tiny hole at 5. So it looked like this on a number line. So this is going to be minus infinity to 5, parentheses, union 5 to infinity. So everything works except 5, and 5 doesn't work because that's when this would equal to 0 and we don't have an equal bar. Okay, so when we had our zero cases here, we had less than or equal to, greater than, and greater than or equal to, and all four of these give you different types of solutions. Okay, so you have to be very, very careful when you're looking at the zero cases. All right, on the very last page here, I just have a summary of all the different cases that we've looked at. So I'm just going to talk you through them. In the first two cases here, or actually the first four cases, you're dealing with A being a positive number. So you're comparing an absolute value inequality to a positive number. So this is like those first problems we did. If you see a less than or equal to sign, then you're going to be setting up a triple inequality where you take the expression that's on the inside and you squeeze it in between this number and its opposite. So whatever A is and minus A. So whether you have less than or equal to, you're going to get these two triple inequalities. If you have a positive number on the right-hand side, but you have a greater than or equal to symbol, then this is where you get the two tail pieces. So this is going to be the case where you have negative A and you want everything to the left, or positive A and you want everything to the right. Up above here was where we had negative A and positive A, and we wanted everything in between. And these can be open circles or closed circles, depending on whether you have that equal bar. So to get the interval on the left, you set your expression, whatever you see inside the absolute values, less than minus A, or to get the interval on the right tail piece, you set your expression greater than positive A. And you might have to do some solving with these. Okay? So you do exactly the same thing with the greater than or equal to case, but you get to include that endpoint. So these first four are going to be when A is positive, when you're comparing an absolute value to a positive number. The next four are going to be when you're comparing an absolute value to a negative number. So when you have less than a negative or equal to a negative, that's the first two, or greater than or equal to a negative. So in the first two cases here, when you have your absolute value less than a negative or equal to a negative, these are both going to be no solution. And the reason why is because we're basically being asked to find out when is the distance less than A. And if A is negative, you can't have a distance that's less than a negative. So that's why these are both no solution. In the greater than or equal to case, you're asked to find when is the distance greater than a positive number, greater than a negative number, and distance is always going to be greater than a negative number because it's positive or zero always. So that's why my two solutions here are all real numbers. Okay? The last four cases here are going to be when you are comparing an absolute value to zero. And here you have four different possible scenarios. If you have strictly greater than zero, then this is asking for where is the distance greater than zero. And that is always going to happen except where the distance might equal to zero. So this is going to be always except where the distance equals to zero. So if you set your expression equal to zero and solve, I called that number K. So K is the solution that you get when you set that distance to zero. So your answer needs to be all numbers except that K value. So you get a solution that looks like this: minus infinity to K, union K to infinity. So it's that case where you just get a little tiny hole at K, but everything else works. Okay? When you compare an absolute value greater than or equal to zero, this is asking for where is the distance greater than or equal to zero, and that's always going to happen. Your distance is always positive or 0, so that's why our solution is all real numbers. For the case where we set our absolute value less than 0, this is asking for when is your distance going to be smaller than 0, and your distance is never going to be smaller than 0 because smaller than 0 would be a negative number. So this is no solution. Then the very last case is when you set your absolute value less than or equal to 0. So this is asking for where is the distance less than or equal to 0, and you're never less than 0, but you could equal 0. So your solution here would be never except when the distance equals to 0. So if you set your distance to 0 by letting your expression equal to 0, if you solve that, and I called that k again, so whatever you get when you solve for this set equal to 0, I called that k, then your answer is supposed to be nothing except that number. So your solution just looks like k. So your only answer is that single number. That's the only number where this is going to be true. Okay? So if you're a memorizer, you can memorize all of these different cases. There's lots of them, so it's a lot to keep track of. Or else you can just memorize bits and pieces and kind of work your way through the rest of them by writing out sort of in words like I have here whether or not you want your distance to be bigger than 0, less than 0, bigger than a negative, less than a negative, or that sort of thing. So there's a lot to keep track of. These are kind of confusing sometimes, but practice does make perfect. And you just want to kind of go through this summary and make sure you understand all the different cases. All right, that concludes our notes on absolute value inequalities. Good luck.